So in this lecture, I will discuss the total variation distance and coupling. So remember that if we have two probability measures mu and u on a finite space omega, we define the total variation distance between mu and u as the supremum or the maximum of mu a minus mu of a, and this for all subsets A in omega, and that we proved that this total variation distance can be written as 1/2 of the sum of x in omega of mu x minus nu x. So now I want to define a coupling between two probability measures. So I would say that P, which is a measure, a probability measure on omega times omega, it's a coupling of mu and u if the following holds. Well, if the first marginal of P it's mu and the second marginal of P it's u. So I would say that it's a coupling of mu and nu. So mind that mu and nu are probability measures on omega, while P it's a probability measure on the product space. Well, if, as I said, P, the first marginal of P, it's mu, which means that for all x in omega, mu of x, it's equal to the sum in y of omega of P xy. And if the second marginal of P, it's nu, which is that for all y in omega, nu of y, it's equal to the sum for x in omega of P xy. And of course, coupling measures always exist. Yeah, here is a simple example of a coupling measure. You can take just the product measure. So define Pxy as mu x, mu on y, and you have, you can check that these two identities are satisfied. So if you have, if I say that you have a set here omega, here is omega, and we want to construct a measure with P with given marginals mu and nu, well, a natural question is maybe to define the measure P which concentrate which maximize the measure on the diagonal. So a natural problem could be to construct a coupling, decoupling, which maximize the measure of the diagonal. So let me call the diagonal D as the sets of xy in omega square such that x is equal to y. Let me call couplings C mu nu the set of all probabilities which satisfy these two equations. So C mu nu will be the set of couplings between mu and u. And as I mentioned, once you define such a coupling, a natural question is the following. You would like to solve the following problem. Take the supremum of P of D. So what is the coupling which maximizes the probability of the diagonal among all P in C mu nu? So what is the P which maximize this quantity, the probability of diagonal among all couplings? And this is, well, a simple question which I will address now. And here is the proposition which answers to this question. So let me fix two probability measures, mu and u. So these are probability measures on a finite space omega. And what I claim is that the total variation between mu and u total variation, that this is equal to the infimum of the measure of the complement of the diagonal among all couplings between mu and u. So we know exactly what is this quantity. So if you want to minimize the measure of the complement of the diagonal, which means that you want to maximize the measure of the diagonal, well, this is exactly given by the total variation between mu and u. So the proof is as follows. I will first consider fix P, which is a coupling between mu and u. And now fix a set A in subset of omega. So what we will prove is actually that this total variation distance is less or equal than this infimum. So let me fix a subset A of omega, and let's consider mu A minus mu of A. Well, let me define now a function x which goes from omega to omega, which just gives me the first coordinate of a point. So x sends the couple xy to x, and let me represent by y the function which sends a couple to its second coordinate. So what is mu of A? Well, since P is a coupling of mu and u, I can rewrite this quantity as the probability that x belongs to A. Because we have seen that the first marginal of P, it's mu. And since the second marginal of P, it's nu, I can rewrite that probability as the probability that y belongs to A. So we can express this difference in terms of the measure P. Now I can rewrite this difference as the probability that x belongs to A and y does not belong to A, plus the probability that x belongs to A and y belongs to A. And I can perform the same decomposition for the second term. So in the second term, I'll get minus the probability that, say, x does not belong to A and y belongs to A, minus the probability that x belongs to A and y belongs to A. Now you see that these two terms cancel, and I can bound this expression by the probability. Well, since this is negative, this is bounded by the probability that x is in A and y is not in A. And this is bounded by the probability that x is different from y. But the set at which x is different from y, it's exactly the complement of the diagonal. So this is equal to the probability of the complement of the diagonal. So these are all points for which the first coordinate is different from the second, and this is exactly the complement of the diagonal. So we obtained a bound for mu A minus mu A in terms of the probability of the complement of the diagonal for any coupling P. So we never used a particular property of P in this computation. Well, and the same computation, of course, gives me, I can replace the role of mu and u. So I can get that mu of A minus mu of A. It's also bounded by this probability. So I have here a number and minus this number, which are bounded by a non-negative number. So I deduce from these inequalities that the absolute value of mu A minus mu of A, it's less or equal than the probability of the complement of the diagonal. And since this inequality holds for all A, I can just maximize that over all subsets A to conclude that the total variation between mu and u is bounded by the probability of the complement of the diagonal. And since this inequality holds for all probability P, which is a coupling between mu and u, I can minimize over that to conclude finally what I claimed before is that the total variation distance between mu and u is bounded by the infimum of the probability of the complement of the diagonal, where I'm taking here the infimum over all probabilities which are couplings between mu and u. So this proves indeed, as I claimed before, that this total variation is bounded by this infimum. So now, if we want to prove this proposition, it remains to show that there exists a coupling such that the probability of the complement of the diagonal is equal to mu minus mu total variation. Right? So we proved this inequality. Now, if I can show that there exists a coupling P such that the measure of the complement of the diagonal is exactly equal to the total variation between mu and u, what we'll prove is that, therefore, if there is one, the infimum is bounded by this quantity, and from this we will have the equality. Actually, we will construct explicitly this probability. And so this is the next step. So at this point, I want to construct a P, which is a coupling between mu and u, such that the probability of the complement of the diagonal is equal to the total variation between mu and u. So I need some notation here in order to prove that, to construct. So let me call A mu. So this is a subset of omega, and these are the points x for which in omega such that mu of x is strictly larger than mu of x. And in the same way, A of nu will be the set of points x in omega such that mu of x is strictly larger than mu of x. And A0, remain the other points, so the points at which mu of x is equal to mu of x. And so now, if I sum over x in omega of mu x minimum of nu x, so let me compute this quantity. Well, I will decompose according to these sets. So that will be the x in A mu. So on the set A mu, mu, it's larger. And since I'm taking the minimum, this is mu x. So mind, I didn't say it, but this represents the minimum between mu x and nu x. So in A mu, this is nu x. Let's say that in A0, they are equal, so I can take any of them. And then on A nu, this is mu of x. So now let me sum and subtract the quantity that this is x in A nu of x. Let me sum and subtract this quantity, and you see that, well, since this is a partition of the set omega, once I sum in A mu, A0, and A nu, nu of x, what I get, since nu is a probability measure, it's 1. And then I have plus this quantity, which is the sum in A nu of mu x minus nu x. And I can rewrite this as 1 minus the sum for x in A nu of mu x minus mu x. And we have seen in the previous lecture that this quantity here corresponds exactly to the total variation. So I'm summing over all points x at which nu is larger than mu. I'm summing the difference, and we have seen that this is exactly the total variation. So this is 1 minus the total variation between mu and nu. And from this computation, I conclude that the total variation is equal to 1 minus this sum. So my conclusion is that the total variation between mu and nu is equal to 1 minus the sum for x in omega of mu x minimum mu x. That's fine. Please keep in mind that. So let me call maybe p this quantity. So this is small p, and we will use this identity in order to construct this measure p. The idea, well, I can write it here. So here is our set omega times omega. Here is the diagonal, and here is a point x. So the sum here has to be equal to mu of x, and the sum here has to be equal to nu of x. So it's clear that the value of this point, so p of xx, has to be smaller or equal than the minimum. Right? Because since the sum here has to be equal, let's say that mu is smaller than nu. So since the sum here has to be equal to mu of x, well, this point can be at most mu of x. And what we will prove is that actually we can define the p on the diagonal through this equation with an identity here. So that will define the measure on the diagonal, and this is clearly the way at which the measure of the diagonal is as big as possible, because it can't be larger than that. It has to be smaller. And the problem is to extend this measure to the complement of the diagonal in such a way that mu and nu will be both the marginals. And so this is the idea. We define this measure on the diagonal, putting as much weight on the diagonal as possible, so putting this weight on the diagonal, and then extending this measure to the complement of the diagonal in such a way that mu and nu are the marginals. So this is what we are doing next. So I kept on the board the sets I will need in this proof, in this construction. So A mu, remember, is the points at which mu x is strictly larger than nu x. Here they coincide, and here nu x is larger than nu x. And then I define by p this sum, and we show that the total variation between mu and nu is equal to 1 minus p. Mind that p it's of course strictly larger than 0, because, well, there will be a point, well, it could be 0, sorry, it could be 0 if mu x is 0 whenever nu x is positive, and the inverse. And it's also bounded by 1, because, well, this is bounded by mu x, and the sum is equal to 1. So it's clear that p is between a number between 0 and 1. And what I claim is that if p is equal to 1, there is nothing to prove, because if p is equal to 1, that means that mu is equal to nu, right? Because if there is a point x at which mu x is strictly smaller than mu x, then this sum cannot be 1. So if p is equal to 1, mu is equal to nu, and then it's very easy to construct a measure, because you just, if mu is equal to nu, you see that the total variation is 0, and then and you can put the total mass on the diagonal. So at point x, you just put a mass nu x at the diagonal, and you see that since mu is equal to nu, the first marginal it's mu, the second marginal it's mu, and therefore you have a coupling. The mass of this coupling is concentrated on the diagonal, so therefore outside of the diagonal, the measure outside of the diagonal is 0, and this coincides with the total variation between mu and nu, which is 0. So if p is equal to 1, the statement is trivial. So what is the statement? Well, we claim that there exists a p in C mu nu such that p of the complement of the diagonal it's equal to the total variation distance. And what we just proved is that if p is equal to 1, this holds because the total variation is 0, and you can construct a measure concentrated on the diagonal. So I can always assume that p, and I will do that, I can always assume that p is strictly less than 1. So let's draw a picture again. So we have here, we divided the set omega in 3 pieces, A0 and A nu. So here's A mu, A0 and A nu. So there's the diagonal, very badly drawn. So on the diagonal at the point x, so p of xx, it's equal to mu x infimum of nu x. So this is the definition of the measure at the diagonal. And well, here on the set A mu, mu x, it's larger than nu x. So at this point here, I need to put some mass on this line, because the minimum here is nu x, and I need that the sum on this column is equal to mu x. So I need to put some mass on these points, because otherwise the first marginal will not be equal to mu x at this point. And here on the set A nu, the same thing occurs. So the mass here, it's the minimum, but the minimum at this point it's mu x, because on this point, let me call that y. So let's say that here it's the point y, y. The mass on the diagonal, it's mu of y, because, well, y belongs to the set A nu, and on the set A nu, mu, it's strictly smaller than nu of y. And this means that I need on this line to put some more weight. And the idea will be, well, to put all the weight on this portion of the set here. So on the set A mu times A nu. So I have here a set x, y, which belongs to A mu, A nu. And what is the mass we will put on this point? Well, this is 1. What I'm proposing is to put 1 minus p, mu x minus mx, mu y minus my, where m is now representing the minimum. So mx, it's equal to mu x minimum nu x. And this is for points x in A mu and y in A nu. Mind that if x does not belong to A nu, if x belongs to A0 or to A nu, well, this difference is 0. And on the other hand, if y does not belong to a nu, this difference is 0. So actually, I can just extend this definition to my whole set, so to the complement of the diagonal, but this is 0 at all points except on these points, on the points xy, on the pairs xy, at which x belongs to a mu and y belongs to a nu. Otherwise, this quantity here is 0. So this is the definition on the diagonal, and this is the definition outside the diagonal. If xy belongs to the complement of the diagonal, we define it in this way. Well, now what I claim, and now what I will prove next, is that the first marginal of P is equal to mu. So what we need to do is we need to sum over all y in omega pxy and show that this quantity is equal to a mu x. So I claim that this quantity is equal to mu of x. This is what I need to prove. Mind that p is non-negative. I'm assuming here that p is smaller than 1, so this is well defined. This is the minimum, so it's non-negative, so p is non-negative. And now what I claim is that the first marginal is equal to mu, and the same computation will show that the second marginal is equal to mu. So let's compute that. Well, I have here that y pxy, so let me take y equal to x, because the definition at the diagonal is different from the definition out of the diagonal. So we have pxx, and pxx, it's equal to the minimum of mu x and nu x. Now, plus the sum for y different from x of mu x minus mx nu y minus my. So let me now divide in 3 cases. Let's assume that x belongs to a nu. So if x belongs to a nu, this means that mu x is smaller, or maybe union a0. So this means that mu x is less or equal than nu x, and therefore this quantity here, it's mu x, because mu x belongs to the set, which means that mu x is less or equal than nu x. And since mu x is equal to mx, this quantity here is 0. Because mx is the minimum, and the minimum is equal to mu x. Which means, well, that the sum is equal to 0, because all terms are multiplied by 0, and this is equal to mu x, so that proves that indeed this sum is equal to mu x, provided that x belongs to this set. So if x belongs to this set, this identity is easily obtained. So now let's assume that x belongs to the set A mu. Since x belongs to the set A mu, this means that nu x is strictly smaller than mu x. Which means that, so now let me continue under the assumption that x belongs to A mu. So this means that this is equal to nu x. Now I have 1 plus 1 minus p. Let me take out this quantity, and mx is nu x, so this is nu x minus nu x, and we have a sum of all y different from x of nu y minus my. Okay. So I can, if I add y equal to x, since x belongs to a mu, this means that the minimum is equal to y, and therefore this quantity here is 0. So I can add the term y equal to x to this sum, because in this case, since x belongs to a mu, the minimum is nu x, and therefore mx is equal to nu x. So I can add the term, so actually this is a sum for all y's. And now, if I recall that my is the minimum between mu y and yi, I also realize that I can restrict my sum over the terms at which mu y is strictly larger than mu y, and this is the set A nu. Right? I had before a sum over all y's, but since this is equal to 0 whenever y does not belong to a nu, I can restrict my sum to the set a nu. And when I restrict my sum to a nu, I can replace m of y by mu of y. And after this replacement, here I get exactly the total variation distance between nu and mu, because I'm summing over all points at which nu is larger than mu, and I'm summing the difference. So this gives me the total variation. So this quantity here, it's actually the total variation. So that gives me that this is equal to nu x plus 1 minus p mu x minus nu x times the total variation between mu and nu. And we have seen that the total variation between mu and nu is 1 minus p. So this quantity will cancel with 1 minus p, and what remains is nu x plus mu x minus nu x. So this is equal to mu x. And this proves that indeed the first marginal of p is mu. So we have proved my claim that the first marginal of p it's mu. The second marginal, of course, it's nu by the same computation. And this shows also that p is a probability measure. That p is a probability measure. Because if I sum, I already checked that p is non-negative. Now if I sum over all x and y p x y, I can first sum over all y, and this will give me the marginal at x of p, but this is mu, and mu it's a probability measure, so this sum is equal to 1. So this shows that p is a probability measure whose first marginal is mu, second marginal is nu, and therefore what we have seen, what we have just proved, is that p it's a coupling between mu and nu. And now, well, what is the probability of the complement of the diagonal? Well, that we have seen. This is the total probability minus the probability of the diagonal, but the probability of the diagonal is the sum of all points of the measure of the diagonal pxx, but pxx it's equal to the minimum. And we have seen that, well, p, so that this quantity here, it's p, so this is equal to 1 minus p, and 1 minus p, it's the total variation. Between mu and u, and therefore, indeed, we just constructed a coupling whose measure of the complement of the diagonal is given by mu minus nu, the total variation of mu minus nu. So this completes the proof of the proposition. Now, my second proposition concerning total variation distance concerns now Markov chains. So let's say that xn, it's a Markov chain, discrete time Markov chain, which is aperiodic and irreducible. So let me represent by pi the stationary state, so the unique invariant measure for this Markov chain. And what I claim is that there exists an alpha strictly smaller than 1 and a finite constant C0, such that if I take the total variation distance between P n x dot minus pi, so this is the distribution at time n starting from x. I consider the total variation with respect to this distribution and the measure, the stationary measure. I claim that this is bounded by C0 alpha to some power, to the power n, where n is the time. And so this is the claim. So this proves what I said in the previous lecture, that the total variation distance is decreasing exponentially fast to 0. Of course, the problem here is that this proposition doesn't give you an explicit formula for alpha. So alpha can be very close to 1. It will depend on the state space. If the state space is very large, it can be really close to 1. Therefore, you know it converges to 0, but you don't have a bound on alpha. This proposition doesn't provide a bound on alpha. So let's prove this result. So it's theoretically it's important, you know that it converges, but in this distance, but well, you don't have an explicit formula for alpha or an explicit bound for alpha. Well, since you know, so let me represent by, I think it's clear, by pkxy. So this is the transition probability at time k. So it's the probability that's starting from x, at time k you are at y. And you know that this is p k xy. So p is the transition probability at time 1, and p to the power k, it's the product of p with p k times. So since the chain is aperiodic and irreducible, you know that there exists a finite r such that p r xy, it's strictly positive for all xy. So this is a consequence of the aperiodicity and the irreducibility of the chain. So now let me introduce a new matrix, which is pi. Well, see, this is capital pi because it's a matrix, while this is a measure. And this matrix pi xy is just equal to pi of y. So pi, it's the measure, and so this is a matrix whose lines are all equal, and they are given by the probability measure pi. So since this is strictly positive, what you see is that you can get a positive alpha such that PR, it's strictly larger than delta pi. You can adjust delta, so this is a strictly positive matrix. Pi, it's bounded, a bounded matrix. So if you take delta sufficiently small, you'll have that this inequality, which means that PRXY, it's less or equal than delta pi xy for all xy. So there exists such a delta. And so let me call theta 1 minus delta. So theta, it's a number between 0 and 1. And let me introduce a new matrix by this formula. So this is equal to 1 minus theta pi plus theta q. So theta, it's 1 minus delta. So if you wish, this is delta. So PR minus delta pi, it's non-negative. So this means that Q, it's the non-negative. This is an equation for Q. So this is the definition of a matrix Q. And what you know is that Q x, y, it's non-negative because PR, it's larger or equal than delta pi. And also that if you sum over y, so now if you consider this matrix xy and you sum over y, you get 1. For this one, you also get 1 because you sum over y this matrix, you get always 1. And this means that for all x in omega, the sum of qxy, it's equal to 1. So the sum of qxy, it's equal to 1. So q are non-negative, the sum it's equal to 1. This means that q, it's a transition matrix for a Markov chain. So that's fine. So this is the definition of P. And now I want to make some remarks about the product of Q and pi. So I want to say that Q pi, it's equal to pi, and that this is also equal to pi Q. So I claim that these, so let's say that this is claim 1. I claim that this identity holds. So in order to do that, well, let's take a product of pi with respect to R and pi with respect to pi to see what we get. So PR pi at xy. So let's say that I'm first proving that identity. So in order to do that, what I'll take a product of pi on both sides of this identity and see what we get. So this is the sum for z in omega of PR x z pi z y. But, well, this is equal. Pi z, it's the matrix which it's constant among the lines. So this is actually p of y, pi of y. It doesn't depend on z. So if I take the sum over z here, I get 1. So this is equal to actually pi of y. And pi of y is pi xy, because pi depends only on the second coordinate. So we see that the product of pi r with pi, it's equal to pi. And the same thing will tell us that the product of pi with pi, it's equal to pi. So let's compute that. So this is a sum over z of pi x z pi z y. But pi depends only on the second coordinate, so this is pi of y, and this is pi of z. Pi, it's a probability measure, so if I sum over z, I get 1. So this is pi of y, and pi of y, it's equal to pi xy. So I get that these two products give me pi. Fine, so I will erase these two identities. So what I proved is that this identity holds for q equal to PR and for q equal to pi. So if I take a product on the right with pi, what I get is that pi, so I'm taking pi on the right, equal to 1 minus theta pi squared, but pi squared it's pi, plus theta q pi. And you see that this pi will cancel with this one. Then we have theta pi, it's equal to theta q pi, and from that we conclude that pi, it's equal to q pi. So this is the first identity I claimed. now we can prove exactly in the same way the second identity. So maybe, okay, to be complete, let me compute pi PR xy. So this is the sum over z of pi x z pi r z y. Now pi depends only on the second coordinate, so this is z, pi z, pr zy, and now pi is the stationary state for the transition matrix PR. So you see that you are starting with a stationary state, but let the process evolve up to time r. So this is equal to pi of y, and this is pi xy. So again, we have shown that pi r, it's xy, it's equal to pi x. We also know that pi pi xy, or pi pi, it's equal to pi. So pi, it's a projection. And so now let's prove the second identity. And for the second identity, I will take pi on the left-hand side on this, both sides of this equation. So pi r, okay, so what we get is that this is pi PR, that this is equal to 1 minus theta pi square plus theta pi q. So this is again pi. This is again, this is also pi plus theta pi q. And from this identity, you see that pi cancel with this pi, and that we get therefore that pi q is equal to pi, and this is the second identity. So we have these two identities. That's nice. So this is the first claim that we just proved. Now let me go to the second claim. And the second claim is that, well, by induction, we will take the powers on both sides of these identities. These equations will allow me to compute these identities. So my claim here is that if I take Pjr, so that this is equal to 1 minus theta to the power j pi plus theta to the power j q. So this is my claim that for all j larger or equal to 1, this identity holds. For j equal to 1, this is the definition of q. So now let's assume that it's true for all j, it's true for j larger than 1, and let me prove that it holds for j plus 1. So pi j plus 1 times r, it's equal to pi r j times pr. By induction, the induction assumption pi jr, it's equal to 1 minus theta j pi plus theta j q, and pi r, it's given by this equation. 1 minus theta pi plus theta q. And well, now let's compute this product. We have this product, and pi square, we know that pi square is pi. So this gives me 1 minus theta to the power j 1 minus theta pi. So this is the first term. Then we have this term, which is 1 minus theta j theta. And here I have pi q, but pi q, it's pi. Then we have this term. So this term, it's 1 minus theta theta j q pi, but q pi, it's pi. And finally, we have the last term, which is theta j plus 1 q. And well, now all the first three terms are equal to number times the matrix pi. And so let's say what we have here, I have 1 minus theta j multiplying 1 minus theta plus theta. So this is 1 minus theta to the power j. So this is contribution of the first two terms. And then I have this last term, which is theta j minus theta j plus 1. So plus theta j minus theta j plus 1 pi plus theta j plus 1 q. And you see that here the minus theta j cancel with theta j, and I get that this is 1 minus theta j plus 1 with j plus 1, so 1 minus theta j plus 1 pi plus theta j plus 1 q. So this proves by induction that this formula holds. And so now with this, we can more or less conclude. So I first would like to estimate pi jr x y minus, so you see that if I take that minus pi xy, this is equal to theta j q minus theta j. Or maybe let me write it in this way. So I can rewrite this identity as pi j r minus pi, that this is equal to this quantity. And so if now I multiply that by some number s, which is between 0 and r, so if I take number s between 0 and r, what I get is that pi j r plus s minus, if I take pi ps, so I'm multiplying on the right ps, but pi ps it's equal to pi. So this is equal to minus theta j pi plus theta j q pi s. Fine. So now we are ready to obtain a bound on the total variation distance. So I want a total variation distance between pi jr plus s starting from x minus pi total variation. So this is equal, we have seen, to 1/2 the sum over y of pi jr plus s xy minus pi of y. And now let's use, and maybe take inequality, so let me use this identity for that. So this is a non-negative matrix, so I get a plus sign here. This is also a non-negative, so that gives me a sum over all y of theta j pi y, xy, but mind xy, it's equal to y, plus theta j q ps xy. But now, mind, if I sum over y py, this is 1, so I get theta j. and Q, it's a Markov matrix, transition matrix, PS, it's a transition matrix, so if I sum over all y here also, I get 1. And since I have a 1/2 here, what I obtain is actually that this is less or equal than theta to the power j. And this bound does not depend on the initial point. So what we proved is that the maximum for x in omega of pi j r plus s of x minus pi total variation distance, that this is bounded by theta, which is a number smaller than 1, to the power j. So if I call this quantity here n, so n it's g r plus s, what I get is that j it's equal to n minus s divided by r, and so the transition Pn x dot minus pi in the total variation distance, and I have here maximum over all x in omega, that this is bounded by theta n over r 1 over theta s. S over r. So s, it's bounded by r. 1 over theta, it's bounded by 1, so 1 over theta, this is a positive constant. So this is bounded by the largest value of s. The largest value of s, it's r minus 1. Say that this is bounded by r. So this is 1 over theta, bounded by 1 over theta, theta n to the power r. So this is the constant I was alluding to before, and alpha, so in my equation here, C0 it's 1 over theta, and alpha it's theta to the power 1 over r. And as I said at the beginning, well, we don't have an explicit equation for r or for theta, so we don't have an explicit formula, an explicit bound for alpha. But we proved at least that if I take the maximum over all x in omega, this quantity here converge exponentially fast to 0. So this is the result we just proved, and in view of that, we will define what's called the mixing time. So fix an epsilon between 0 and 1, and I will define the epsilon mixing time, so T mixing epsilon. I know that this maximum converges to 0, so it will be bounded by epsilon for n sufficiently small. So this is the minimum over all n larger than 1, such that the maximum of x in omega of the total variation Pnx minus pi total variation, that this is bounded by epsilon. So it's the first time at which, whatever starting point, the distribution of the chain at time n, it's at distance in the total variation sense less than epsilon from the stationary state. So it's T mixing tell you how long you need to wait for the distribution to be close to pi at distance epsilon in the total variation distance for all initial states. And this is what we would like to bound? We would like to say, well, that to have an upper bound of the mixing time, so that the mixing time cannot be very large. It's bounded in our examples by a certain quantity which you can estimate. So this is the quantity. Well, we want to estimate this difference. We want to estimate how close we are from the stationary state in this distance, and the quantity which we will state is about mixing time. So the mixing time of certain chain, it's bounded by that or that quantity. This will be the goal of the remaining part of this lecture at least. So let me return to the original problem. The original problem was that we had a certain space, omega. We had a measure omega in this space, a probability measure, and we wanted to simulate this measure. So we want to find random variables whose distribution is given by pi. And the idea we propose is to construct a Markov chain, which is aperiodic irreducible and which has pi as unique invariant state. And the idea was to run that chain for a very long time and to claim that after a very long time, n, the distribution of the Markov chain would be close to pi. Of course, the problem is, there are two problems. The first one is that the distribution of xn, it's not really equal to pi. It's close to pi. We have seen here a bound for a Markov chain, aperiodic and irreducible. So it might be very small, but it's not exactly equal. So what we'll have is that the distribution, if I'm allowed to write xn as the distribution of xn, that this is small. But that's fine, because we don't really want the exact distribution. Something very close would be fine. But the second main problem is how large we need to take n. And, well, we have seen here that the mixing time tells us how large we need to take n. If we want this total variation to be bounded by epsilon, the mixing time tells us what is the size of n we need to take. But how to estimate the mixing time? And this is what I want to start discussing now. Actually, we will concentrate on one example which explains a possible strategy in order to estimate these mixing times. And this strategy is based on coupling. So I want to talk a bit about coupling before we start with the example. We have seen a coupling between two measures. So if I have mu and nu, two probability measures, we have seen defined the coupling between these two measures. P, it's a measure on the product space whose marginals are equal to mu and nu. Now, I want to extend this concept to process, to Markov chains. So let's say that we have two Markov chains, xn and yn, and say that to simplify, let's assume that their transition matrix are the same. The only difference is that say that x0 starts from a point x, while y0 starts from another point y. And we would like to couple these two chains. What means coupling of two chains? Well, what we will do is the following. And the idea is very similar to this idea, is that we will define a new process, xn, yn. So again, now the process will, on the product space, omega times omega. And what are the properties? So this defines a new process. Let's say p hat. This would be the transition matrix of this new Markov chain, xn, yn, which is living in this product space. And what are the properties we require? of this chain? Well, what we require is that if we observe the first marginal, so let me maybe put a hat at xn, yn. So let me start again. We start from two Markov chains, xn, yn, defined on the space omega, and I want to define a coupling between these two chains. So what would be a coupling? Well, a coupling will be a new process, x hat and y hat n, defined on the product space omega times omega, and with two properties. The first one is that if you observe the first marginal, so xn, that xn evolves as xn. So remember, for the coupling of measures, we wanted the first marginal to be mu. Now I'm observing a process on the product space. What we require in this coupling is that if I observe, I forget about the second coordinate and I observe only the evolution of the first coordinate, well, the evolution is exactly the one given by xn. So the first coordinate evolves as a Markov chain with a certain transition probability p of x, p. Say that p is transition probability. And also that the second marginal evolves as y of n. So I would say that x hat, y hat, it's a coupling of the Markov chain xn, yn, if these two properties are matched. So x hat, y hat, it's a new evolution in the product space, such that the first coordinate evolves as xn and the second coordinate evolves as yn. And I will give you an example in a second of a coupling between Markov chains. And this coupling will be used in order to estimate the mixing time. So let me go back. So let me give you an example now to illustrate what, how you can use couplings in order to estimate the mixing time. So let us go back to the Q coloring problem. So remember, in the Q coloring problem, we started with a graph G given by vertices and edges, and we constructed, and we have S, which is the set of colors, 1Q, and we define the state space omega as all colorings of these vertices. So this is S to the power V. But what we require is that if you take two vertices which are connected by an edge, the colors of these vertices are different. So I want eta x to be different from eta y for all y which are connected to x. So this is our state space. And pi is the uniform measure over all colorings. So pi of a configuration eta, it's simply 1 over the total number of configurations. Mind that the total number of configurations is quite complicated. And we define a Markov chain, which we call the Gibbs Sampler, which is a periodic whose invariant measure is pi. We didn't prove that it's irreducible. As I said, it will depend on the number of colors. And what we want to do now is to estimate the mixing time of the Gibbs sampler. Actually, not of the Gibbs sampler, but we will use its cyclic version. So remember that instead of choosing at random one vertex, we could also proceed step by step. So assume that the vertex set, the set of vertices, is just enumerated by from 1 up to, let me call that m, the total number of vertices. And what we would do is that we will first update the color of the vertex 1, then the color of the vertex 2, and so on until the last one, and then we repeat. So we have defined this dynamics, the cyclic Gibbs sampler, and we want to estimate the mixing time of these dynamics. So, and for that we will use a coupling. So to explain you the coupling, let me consider a very simple case. Let's assume that the set of edges it's equal to the empty set. So there are, in this starting graph, there are no empty sets, there are no edges, and which means that, say that we have here the set of vertices, say that Vm is equal to 5, so there are no edges. So in that case, the set of omega coincide with all possible colorings. So all possible colorings, which will be s to the power v. Of course, in this case, well, pi, it's elementary. You have q to the power v configurations, and it's very easy to simulate, to extract a configuration drawn from this measure. But I want to explain you the coupling. So in this case, the Gibbs Sampler, so here is the first vertex, here's the last one. So what the Gibbs Sampler would do, it will first choose this vertex, and it will replace this color by a possible color. But here all possible colors, all colors are possible, so you'll just take one color at random and replace the color of this vertex by a color, say, A1. And then it will go, and this will happen with, so the color will be chosen at random, so with uniform probability. Then the Gibbs Sampler will look, the cyclic Gibbs Sampler would look at the second vertex and will update the value of the color of this vertex. Since all colors are possible, he will choose one at random and give this color, say A2, to the second vertex, and so on. So now, assume that you have a process which I'm calling now eta instead of x. So this is eta n is my cyclic Gibbs Sampler, which is starting from a configuration eta. And now I have a second process which is, let's say, has the same dynamics. It's also a cyclic Gibbs Sampler, but it starts from a configuration xi, which is different from eta. And what I want is that I want to define a coupling. So now I want to consider the process eta n xi n. I want them to evolve together in such a way that if I look just at eta, I observe a Gibbs Sampler, just at xi, I observe a Gibbs Sampler. But I want to define, there are many ways in which I could define this coupling. I could just ignore xi and let eta evolve, ignore eta and let xi evolve independently. That would define a coupling. But I want a coupling so that xi n and eta n become equal very fast. So I want to, so remember that in the case of measures, in my coupling, I wanted a measure in which puts as much weight as possible on the diagonal. So now in these couplings, natural problem is to define a coupling such that the probability that xi n is different from eta n, that this is small, if n is large. So I want to define a coupling which make these two copies equal with very large probability. So how would you define this coupling in this trivial case? Well, the idea is very simple. I want to update at step 1 since xi n and eta n are my cyclic Gibbs Sampler, I want to update for eta and for xi the color of the first vertex. So the color of the first vertex for eta, it's eta v1. The color of the first vertex for xi, it's xi v1, because eta n is starting from the configuration eta and xi n starting from the configuration xi. So these colors may be different. But what I can do, if I want to minimize this probability, it's to use the same color to update both processes. So since this color is chosen at random, I can choose one color at random and put this color on the process eta, use that color for eta and for psi. If I observe only eta, what I see is just the cyclic Gibbs sampler, because I'm choosing at random one color, I'm putting this color at vertex 1, so this is exactly what the cyclic Gibbs sampler do. The same thing occurs to psi. If I observe psi, I ignore eta, what I'm observing is that at time 1, I'm updating vertex v1 by choosing a color at random, so this is exactly the cyclic Gibbs sampler, and therefore, if I observe the first coordinate or the second coordinate, what I observe, it's the evolution of the cyclic Gibbs sampler. But if now I look at the pair, what I see is that after the first step, the color at vertex 1 for both processes, it's equal. And if I repeat that, so if I use the same color at time 2 to update the vertex v2 of eta and the vertex v2 of psi, I see that at time 2, both vertices have the same color. And for that, if now I reach at time n, at the last vertex, well, after time m, all vertices of eta will have the same color of psi. So this means that by using this coupling, which uses the same color to update eta and v, what I get is that for the coupling process, psi n, psi m, it's equal to eta m with probability 1. And in particular, well, that will be true for all j's for all times after m. And well, and therefore we have just defined a coupling which gives a very large probability for this event that they are equal and a very small probability for the event that they are different. And this is very, well, this is very interesting because I could use, this is one possible coupling. The second possible coupling is just to ignore what eta is doing to update psi. So psi will use some color b1, some color b2, drawn at random from the set of colors. Well, but after m steps, the colors will be completely different at each vertex. And so this probability could be very large. So very close to 1. So you see that, so my point here is that there are many ways in which you can define a coupling of two Markov chains. I presented here two, but our concern, so our goal here, is to define a coupling which gives very small probability, so which tries to make the two copies equal. So to give a very small probability for having different configurations. So this is what I'm going to do next in the remaining of this lecture for the cyclic Gibbs sampler, but not in this trivial case, but in a reasonable case in which you have edges, and therefore you cannot just repeat that, because of course if you have edges, if this one is related, has an edge with v2, and if the color here is 1, this means that I cannot choose and say that the color here is 2 for psi. Well, I cannot choose color 1 for eta, but I can choose color 1 for psi. So I cannot do exactly what I presented, but we will try to simulate, we'll try to be as close as possible from this idea. So trying to give, whenever possible, the same color to the same edges in our updating mechanism. So this is what I'm doing next for the Gibbs sampler. So here is the cyclic Gibbs sampler, and omega will be my state space, and I will be assuming that there are many colors, so that Q, which is the total number of colors, it's larger than 2d squared. This, well, we can improve on this condition, on this assumption, but I want to make things as simple as possible, so let me assume that indeed there are many, many colors, and because that will simplify the proof. And what I want to do is that I want to define a coupling in such a way that the probability, so the coupling will be pair eta n and psi n, so that the first one evolves as the cyclic Gibbs, the cyclic Gibbs Sampler, as well as the second one, and I want to minimize the probability that they are different. So I want that to be small for n large. And so what is the idea? The idea is that we have a vertex V1, and this vertex V1 has a certain quantity of neighbors. These neighbors, well, for the configuration eta, they have, say, colors eta W1, eta W2, up to eta WP, as well as colors psi W1, psi W2, psi WP. So now I want to update this color. I have to respect all the constraints, so I can't give a color psi omega 1 W1 for psi in this vertex, but maybe I can give it for eta, but I want this color to be equal for eta and psi as much as possible. So we have here one, so the possible colors are 1, 2, and q, and I have to define how I update eta and psi. So for that, let me call R1 a permutation of this set. So it will be a permutation, and so R1 will be just a sequence R1, 1, R1, 2, and up to R1, Q. So this is a permutation of the colors, and the idea is that I started from eta, and I will look at, in this permutation, at the first allowed color. So I look at the first color, I see if I can use this color, so if it satisfies the constraint. If it satisfies the constraint, this is the color I put for eta at vertex eta 1. And I will use the same permutation to update psi. So I look at this sequence, I'll see if the first color it's allowed. If it's allowed, I will use it. If it's not allowed, I'll go to the second color and so on until I'll find a color which I'm allowed. Of course, since Q is larger than D, there is always a possible color, so this procedure will always give me a color to update. So let me repeat. I have this, I fix a permutation. I want to update site V1. I will use this permutation R1 to update site V1. So this is a random permutation. There are Q factorial permutations. Each one has the same probability. And now if I want to update eta, I will look at this permutation. I look at the first term. I see if it's an allowed color, I use it. If it's not, I go to the second. If it's an allowed, I use it. Otherwise, I go to the third, and so on. And I do the same thing for psi. Now, let me look at, so now I want to define a partition of the set S. So A0, A1, A2 will be a subset of 1Q, and they will be the intersection of these sets will be empty. So it's a partition. So A0, it's the subset of colors which are not used by neither by eta or xi on the neighbors. So A0, so let me define it. A0 is all so A in S such that eta W it's different from A for all W neighbor to V1, and xi W it's different from A for all, so W1, W2, W1, and W2 for all. No, okay. So eta W should be different from A for all neighbors of V1, and xi of W should be also different from A for all W. So these are the colors which are not used by the neighbors neither for eta nor for xi. So eta and xi do not use the colors in A0 on the neighbors of V1. So A2, it's the set at which both have a neighbor which are used. So these are all colors such that there exists omega 1 W1 which is neighbor to V1, and eta of W1 it's equal to A, and there exists W2 neighbor of V1 such that xi W2 it's equal to A. So these are all colors which are used in the neighbors both by eta and by xi. So I can find the neighbor W1 of V1 whose color it's equal for configuration eta to A, and another neighbor which might be the same but might be different, whose color it's also A for the configuration xi. And A1 it's the complement. So A1 it's S minus A0 union A2, and these are the sets of colors which are used by one configuration, either by eta or by xi. So I hope that this is clear, and so that these sets A0, A1, A2 are well defined. Okay. So 0, no neighbors. 1, there is one configuration which use it. Both configurations use that color. So mind, A1, if I count the total number of elements of A1. So these are, let's say that I'm taking A1 here, A1 here. So these are colors. Well, let's set the number of neighbors which use one color, plus 2 times A2, that this should be less or equal than the total number of neighbors of eta times 2. So this is bounded by 2 times d of eta 1. Of course, now I just realized that I didn't tell you what's d, and here I'm defining d of eta 1. So d of eta 1, it's the degree of eta of a configuration d of v, d of v1. So I'm sorry, d of v1, it's the degree of v1. So it's the number of neighbors of v1 for the graph G. So remember, there is a graph V and E in the definition of this model, and d of v1 it's the degree of the vertex v1, and more generally d of v it's the degree of a vertex v, and this is the total number of neighbors of this vertex for the graph VE. So this defines dv, and now I can define d. So d is the maximum degree. So d of the graph G, it's the maximum of dv for V in V. So it's the maximum degree of the graph. And this is the D which appears in the assumption, and I'm assuming that Q is larger than 2 times the degree, the square of the degree of the graph. Now, let me go back here. I defined A0, A1, A2, and what I'm claiming is that the total number of points in A1 plus 2 times the total number of points in A2, it's bounded by 2 times the number of the degree of V1. So the degree of V1 tells me how many neighbors there are. 2 times it's because I can have a value for eta and psi. And well, A1 tells me the number of neighbors which have one color, whose color it's used by eta. And so here I'm counting exactly the number of points in which one color it's used by either eta or psi, but just one color. And then A2 counts, so this is the number of sides. So each side has 2 colors. This color can be used once or twice. If it's used twice, it enters in A2, and this is why I have 2 times A2. And if it's used once, well, it is in A1. So this is actually equal to 2 times the number of the degree of V1, the number of neighbors of V1. So now I want to estimate what is the probability that after updating the configuration, so I'm time 1, I want to estimate the probability that the color of vertex V1 for the process eta is different from the color of the process V1. So you have, if the first color, it's a color in the set A2, there is no problem because this color, it's used by both eta and psi in a neighborhood. So this color is not allowed. So if the first color belongs to the set A2, which means that both configurations, eta and psi, use this color in a neighborhood set, I cannot use this color for eta and for psi. So I have to look at the second color. If this second color is in A0, well, then it's very nice because this color does not belong, it's not used by eta, it's not used by psi, therefore I can use it for both. And therefore, in my update, I will be able to use that color, which means that the color of the vertex V1 for eta will be the same. What might happen is that this color belongs to A1. If this color belongs to A1, this means that, well, it's allowed for one of the configurations, but it's not allowed for the other configuration, which means that I will use one which is allowed, but I won't use it because it's not allowed for the other configuration. And for the other configuration, I will have to look further in my permutation. So my conclusion is that the set A2 here is not important because each time a color belongs to A2, I can just ignore that color and go to the next one. The game is played by the sets A0 and A1 because A0 gives me a success, so if the color belongs to A0, I can use it for both. But if the color belongs to A1, I can use it for one but not for the other, and therefore the colors will be different. So the probability that they will be different will be given by the total number of elements of A1 by the total number of the set A0 plus A1. So my coupling will fail, I will have a failure if the color, the first color which appears in my permutation belongs to A1, ignoring A2. So I remove from all colors from which are used by both, so all colors in A2. I keep only the colors in A1 and A0. If the first color belongs to A1, it's a failure, but if it belongs to A0, it's a success. Both configurations will have the same color in the next step. So they won't have the same color if the color chosen belongs to A1, and this happens with probability A1 divided by A0 plus A1. And so now I can use this identity to replace A1 by 2 times dV1 minus 2A2. 2 times dV1 minus 2A2. And on the other hand, A0 plus A1, it's equal to the total number of colors minus the set A2, because these sets forms a partition of the set of colors. So this is Q minus A2. And now I can rewrite this as 2D divided by Q, and mind that because dV1 it's bounded by D, mind that Q is larger than 2D squared, so this is bounded by 1. And what I have here, it's, well, here I have 1 minus A2 divided by D, and here I have 1 minus A2 divided by Q, and I claim that this is bounded by 2D divided by Q. Because, well, this is bounded by 1, this is bounded by 1 if and only if, so let's check. If and only if 1 minus A2 divided by D, it's bounded by A2 divided by Q. This means that, okay, A2 divided by Q, it's bounded by A2 divided by D. And this happens if and only if D, it's bounded by Q. But that's fine because 2D squared is bounded by Q. So this inequality is satisfied. So we proved the following bound is that, well, the update will fail with a probability which is bounded by 2D divided by Q. So I defined a coupling. So I defined a way in which I update at the same time eta and xi. And in this definition, in this way of updating, what I get is that, well, these two configurations get a different color outside V1 with a probability which is bounded by 2D times Q. And now I can repeat this argument. So remember, at step 2, at time 2, I will update the vertex V2. And at time m, I will update the vertex Vm. And at each time, by repeating this procedure, what I get is that, well, the probability that after the updating they have different colors, that this is bounded by 2D divided by Q. So what happens is that up to time m, so remember m, it's the total number of vertices. So when I reach time m, I updated once each vertex, and for each vertex, the probability that they differ, the colors differ after updating, it's bounded by 2D divided by Q. Now I start at time m plus 1, and I will repeat the same procedure. So I'll try to give the same color to eta and xi at vertex eta 1. But now I claim that I can get a slightly better bound, because what is the probability that the color are different? So what's the probability that I fail to give them the first equal colors? Well, you see that if I look at the neighbors of V1, and if the colors of eta and psi coincide at all neighbors, then with probability 1, I can update the colors in such a way that they will keep the same value, the same color at site 1. So let me repeat, if the colors of eta and psi are equal at the neighbors, then I can update the color at V1 in such a way that eta and psi will have the same color after the updating. So the probability that my coloring fails, and by failing means that at time m plus 1 the color at V1 of eta and psi will be different, the probability of failing, so this is the probability that eta m1 at eta m plus 1 V1 is different from psi m plus 1 V1, it's the probability that I fail given that I have a difference times the probability that I have a difference. And by difference, by difference here, I mean that there exists a neighbor of V1 such that eta V1, eta W at time m, it's different from psi at time m of W. So this is the probability that I fail, so that the colors will be different. The colors will be different, the probability that the colors will be different is the probability that they will be different given that one of the neighbors do not coincide times the probability that one of the neighbors do not coincide. Okay? Because if on the complement of this set, so if all colors are the same, I can update in such a way that there is no failure. So this is the probability of the failure. And now I can bound. Well, if they are different, I already seen that the probability that I fail, it's bounded by 2 times d divided by q. Okay? So if I have different colors among the neighbors, so if eta and psi do not coincide among the neighbors, then the probability that my algorithm fails, it's bounded by 2d divided by q. So this is a bound for that. So what is the probability that they differ? Well, the probability that they differ, it's the probability of this union. Well, in this union, I have how many terms? Well, the number of terms is the number of neighbors. The number of neighbors dv1. And this is multiplying this probability, but this probability is bounded by this quantity. So this is bounded by 2dq. And therefore, this is equal to 2dq. And let me bound this by d, and this is multiplied by 2d squared divided by q. Right? So this is the probability that at time m plus 1, the colors at v1 of eta and psi differ. So instead of getting this, what I get is that at time 2m, the probability that they are different, it's not bounded by this quantity, but now it's bounded by 2d divided by q times 2d squared divided by q. And because I can repeat this argument for all vertices vj. Right? And this is why I asked q to be larger than 2d squared to make this quantity here bounded by 1. Right? The argument I used for vertex v1, I can use it for any vertex, and this argument will provide me this bound for the probability that at time 2m, the colors are different on the vertex vj. Now I can repeat exactly the same argument to compute at time 3m. At time 3m, so the probability that it fails, it's kept, given that they are different, it's always given by this one. But now the probability that they are different is changing. It's changing by this factor. So I have D due to the union times the probability that it fails, which is 2q d, 2d divided by q, to d squared divided by q. And you see that this is bounding again d by d, the number of the degree of V1 by the total degree. This is 2d squared divided by q squared. And so at time 3m, this will be bounded by 2d divided by q and 2d squared q to the square, which I can write, if I multiply that by d and I divide it by d, I can write this as 3, 1 over d. And you see that I can repeat this argument and say that if I repeat that r times rm, I will get here r. That's, so I have this bound. I proved that the probability that at time rm, if I fix a vertex vj, the probability that at time rm, the color of the vertex vj for the configuration eta is different from the one of psi, this is bounded by this quantity. So this tells me that the probability that eta at time rm is different from psi at time rm, right? Well, if they are different means that then there exists a vertex at which they are different. There are m vertices, so this is bounded by m, times the probability that they differ at one of them, and this is given by that. And this is, now we have an explicit bound, right? We have an explicit bound which depends on the parameters of our model. Q, the number of, so while in the general theorem we did not have a value for the coefficients which were appearing in the proposition, in this model, by using this coupling, we have an explicit formula to bound that. So let me use this. So we have seen so that the total variation, so let's say that eta, it's starting from some measure mu, which may be a configuration, maybe concentrate on the configuration, while nu, it's starting, psi, it's starting from a measure nu. So an example will be starting eta from a configuration and starting psi from the stationary state. And then, so we'll have that the total variation of, so let's say mu p at time rm minus mu p rm total variation p gives me a coupling. So what I want to say that this is, so since eta it's evolving as the original process, if I look for the coupling at the first marginal, what I get is this measure. If I look for psi for the second marginal, what I get is this measure. If psi is starting from nu. So here, mind, I didn't define, but I hope that's clear. So this is, I'm starting at time 0 from mu. I'm letting the process evolve up to time rm. And this is a new distribution. So this measure, mu p rm at configuration psi, it's equal to the sum over all configuration zeta of mu zeta the probability that I jump from zeta to psi in time Rm. So this is a new probability measure. And what I'm claiming is that if I start at time 0, taking a distribution of eta equal to mu, and if I run this coupling at time Rm, if I project that on the first coordinate, what I get is this measure. The same thing, if I project on the second coordinate, what I get is this measure. So, and we have seen that the total variation, it's bounded, it's equal to the infimum over all possible couplings, but so this is bounded by the probability that eta Rm is different from psi Rm. Observe that in this argument, in my construction, I never used the initial condition of eta or of psi, so I can just take any initial condition, and that this is bounded by m to the d to 2d square divided by q to the power r. So I can here write this as Rm and divide that by m, and this is exactly what's appearing here. And so now this tells me that this difference is decreasing exponentially fast, and if I want an estimate of the mixing time, I want this to be bounded by epsilon, and my question, so let me call that n. My question is, how large has to be n for that quantity to be bounded by epsilon? So this is that, let me take log, so n divided by m, log of 2d square divided by q has to be less or equal than the log of epsilon d divided by m. Now, well, this is a quantity which is smaller than 1, so let me rewrite that as n. Let me multiply by -1, so I get that log of q 2d square has to be larger than log m epsilon d. And so this tells me that n has to be larger than m times log m plus log 1 over epsilon minus log d divided by this quantity, log q divided by 2d squared. So if I want this total variation distance to be bounded by epsilon, I need to take a time t larger than that. If I take a time n larger than that, then I know that this quantity is bounded by epsilon. So this is telling me that the mixing time t epsilon, so let me write it here maybe. So this is telling me, and let me write it in color, this is telling me that t epsilon it's less or equal than this quantity. Divided by log q 2d squared. Right, t epsilon is bounded by this quantity because if I take time n larger than this quantity, then the total variation is bounded by epsilon. And this tells me, therefore, that I don't need to go that far, I can go just before that. So the mixing time is bounded by this quantity. And what's very nice about these formulas, now we have a formula for the mixing time, it's bounded by that. And what you see is that the main term is the total number of vertices. So the mixing time for this sampling is of the order of m log m. So if you want to go up to distance epsilon, so if you want your Markov chain, the distribution of your Markov chain to be at distance epsilon for the total variation with respect to the stationary state, you have to run your Markov chain up to time m log m. Here this is a constant, so you have to add a number in order to make it distance epsilon, but you see that the main factor here is m log m. And therefore, this tells you exactly what you need to do. I mean, if you want to sample pi using this algorithm, the cyclic Gibbs Sampler, you have to run the cyclic Gibbs Sampler at an order of time of m log m, where m is the total number of vertices. So that gives you very precise information, a very nice bound on the mixing time, and gives you an idea how to use these couplings in order to get an estimate of the mixing time.